Okay, so our next chapter is fluids. This is a very important chapter because every year we ask a lot of questions from this chapter in your uh, tests. So, in addition, this is a long chapter and it has a lot of important equations and a lot of important principles to learn. So before we get started, what is a fluid? So we know liquid is a fluid, gas also a fluid. So what is the common, what is the common thing for liquid and gas, or what is a fluid? Uh, a fluid is uh, any substance any substance uh, in which the molecules because fluids made out of molecules, so any substance in which the molecules are free to flow. So free to flow. So if you consider liquid or gas, the molecules, those liquid or gases made out of, are free to flow. Any substance in which the molecules are free to flow, we consider as a fluid. Okay, density of a fluid. We use rho for density. Density. Rho is density. Mass of the fluid divided by the volume of the fluid. So density is mass over volume. So the units of density is units of mass, which is SI unit is kilograms, and unit of volume is cubic meter. So kilograms per cubic meter is the density or mass density of a fluid. This table shows mass densities of some of common materials, solids, liquid, and gases at Celsius 0, Celsius 0 temperature and 1 atmospheric pressure, because when we talk about densities, we have to give the pressure and the temperature, because we know when we increase the temperature, the distance between molecules can change, increasing or decreasing. Therefore, when the volume changes, its density, because density is mass over volume. If volume change, increase or decrease, it can change the density. Uh, we see a couple of common densities for aluminum: 2700 kilograms per cubic meter. If you take water, 1060 kilograms per cubic meter. Mercury is the highest density, 13,600 kilograms per meter cube. Water at 4 degree, 1000. And air 1.29, oxygen 1. The densities of gases you see compared to solids is much lower because it can spread in over larger volume, but solids you see large values, gold 19,000, iron 7,000, lead 11,000. So solids has higher densities compared to gases. Okay, here's a simple example uh, to use this density equation. The body of a man whose weight of a person is 690 newtons and contains about 5.2 times 10 to negative 3 cubic meters of blood, the volume. Okay, this is the volume of blood. find the blood's weight. So the equation is density equals mass over volume. If you know the mass, weight, we use W, which is mass times gravity. If you know the density of a mass, then we can calculate the weight. So from this equation, mass is density over volume, density over volume. So volume is 5.2 times 10 to negative 3 cubic meters, which is given, and density we can look up from the table I showed you in the previous slide, 1060 kilograms per meter cube. So therefore mass of the blood is 5.5 times 5.5 kilograms, and then if you multiply mass by gravity, you get weight. And the second part says it's a express it as a percentage of body weight. So if you know the body weight which is given, and if you calculate the blood weight, you can take the ratio, you can give it as a percentage. So weight is mass of the blood, which we calculate, and the gravity, which is 54 Newton. So the percentage is blood's weight divided by body weight multiplied by 100%. So percentage of the blood, weight percentage of the blood compared to the body weight is about 7%. So in our body, about 7, almost 8% is contribute from the blood, weight of blood. Okay, our next topic is pressure. Pressure is we use uppercase P for pressure, force acting on unit area. Pressure is force acting on an area. So force over area. So unit of pressure is unit of force, which is Newton, we know that. And unit of SI unit of area is square meters. So newtons per meter square. And instead of newtons per square meter, we can write Pascal. So 1 Pascal equals 1 newtons per meter square. So SI unit of Newton is Pascal. Okay, so here the first example, so we learned that pressure P is force over area, and suppose pressure acting on the back of a swimmer's hand is 1.2 times 10 to 5 Pascal. The surface area is given, back of the hand is 8.4 times 10 to negative 3 meters square. Determine the magnitude of the force. Magnitude. We know force is a vector which has a magnitude and direction. First part we need to calculate the magnitude, and then second part it asks what is the direction. So force is from this equation, pressure times area, so P times A. So pressure is given 1.2 times 10 to 5 Pascal, and area is 8.4 times 10 to negative 3 meters square. And you can calculate force, and let me show you the calculations on the next slide. Okay, so pressure is given 1.2 times 10 to 5 newtons per meter square, and area is 8.4 times 10 to negative 3, so this meter squares cancel meter square. So your final answer is in newtons because it's pressure. So 1 times 10 to power 3 newtons, 1000 newtons. Since the water pushes perpendicular against the back of the hand, the force is directly downward in the drawing. So this is the direction, and the magnitude is 1000 newton. Okay, so atmospheric pressure. So pressure is P is force over area, we just learned. So atmospheric, what is atmosphere? So we know atmosphere made out of different gases, nitrogen, carbon dioxide, oxygen, carbon monoxide, argon, water vapor. So the combination of these gases made out of atmosphere. So if these gases contribute to pressure on a certain area, like 1 millimeter, 1 meter by 1 meter area. So these are gas molecules. And if you consider 1 by 1 meter square area, so all these molecules apply pressure. So the magnitude of that pressure, we call it atmospheric pressure. So if you consider 1 meter by 1 meter area, the force on this area is 1 times 10 to 5. So this force acting on this 1 meter by 1 meter area, we call it atmospheric pressure. So that value is 1.013 times 10 to 5 Pascal. Pascal is the SI units of pressure. So we know Pascal is newtons per meter square because force over area. So force from gas molecules on a unit area is the atmospheric pressure. We know atmospheric pressure at sea level is 1.013 times 10 to 5 Pascal. So this is sea level. So what will happen to the pressure if you go deep or if you go up? So we're going to derive a relationship which shows as the relationship between pressure and the depth. So when we to derive this equation, we have to consider a fluid and any type of fluid, and inside that fluid we have to imagine there is a cube in this shape, imaginary cube made out of from the same material. So top side area of the cube is A and the bottom side area is A because it's the same cube, opposite sides, and pressure on the top side we can assume P1. On the pressure on the back side, bottom side, we can assume P2. So we're going to derive a equation, the pressure difference on top and bottom in terms of the given known quantities. So we know from previous lessons, when something is in equilibrium, the total force or net force acting on an object along x direction and y direction is 0. So if you consider a vertical direction in this cube, the pressure, which is force over area. So in other words, we can write a equation for force in terms of pressure and area. So pressure on top, P1 times area is A. P1A is the pressure on top. P2A is the pressure from bottom. And also this cube made out of the same fluid has a density. Therefore, it has a weight because we know density is mass over volume. So if you multiply density with volume, we can get mass. So we know the weight force is mg. So therefore, the mg is rho, density, volume of the cube, times g is the gravity. That is the weight. So if you use sigma fy, forces, net forces along y direction is 0 if this is in equilibrium, which is pressure on bottom P2A minus, because P2A is in pointing up, because opposite positive y direction. P1A is a pressure on top which is pointing down, and the weight force is again pointing down. So these two are negative quantities. P2A is a positive quantity. If these three are in equilibrium, forces are equilibrium, if you add these three together, which is equal to 0. So therefore we can rearrange this equation and we can write P2A is equal P1A plus mg. So mass is, we know, rho, which is density times volume. So instead of mass, we can write rho Vg, which we have here. And volume in this cube, we know the side, which is A, and if the height is h, so V is equal to A, which is side, area of a side, and the height of the box, so A times h. So we can replace V with A and h. I will show you when I apply, rewrite this equation. P2A is equal to P1A plus mg. We're going to replace with A times h times rho, because V equals A times h, and then the density times gravity. Here's the equation we derived in the previous page. Pressure on the bottom, or the force applied on the bottom surface, P2A, is equal to pressure on the top surface plus the weight force, which is pointing down. So volume is area times height. So if you rewrite this equation, P2A is equal to P1A plus rho. Instead of V, we can write A, H, G. So now all three terms has A, which is a common, so it cancels. Therefore, P2 is equal to pressure from bottom is equal to pressure on top plus rho Hg, density of the fluid, height difference between the 2 points P1 and P2, and G. So in other words, the pressure difference P2 minus P1 between 2 points is equal to volume of the fluid, height, and gravity. We learned a equation to compare the pressure and depth uh, in a fluid at two different points. Pressure on bottom is equal to pressure on top plus density of the fluid, height difference between P1 and P2, and the gravity. So in this conceptual example, we going to compare a large water reservoir, and we remove the water from that reservoir and just keep the same depth, but a small amount of water, or very narrow uh, section of water, but keep the same depth. And the question is, now we have very small amount of water compared to a large amount of water in this reservoir, and the question is, do we still need a large wall to hold this small amount of water? So from this equation, we see pressure on bottom of this small water strip compared to pressure one on top is same as the pressure on top of this reservoir and the pressure on the bottom, because this equation is only related to pressure difference P2 minus P1, density, height, and gravity. So the pressure difference is only related to the density and the height. So if the height is still the same, no matter it contains large amount of water or small amount of water, if it is same height, you still have to have the same wall. Otherwise, because of the pressure difference, uh, we cannot keep this water without breaking this wall. So in this example, we asked to find the pressure at point A and point B. So pressure here and pressure here. So according to this equation, pressure 2 is equal to pressure 1 plus rho Hg. So pressure difference between 2 points, let's say pressure 2 at A is equal to pressure difference at point B plus rho Hg. But we know A and B are in the same level, which means H is 0 because it's the same level. Pressure at A is pressure at B. So if we can talking about the points at the same level, it can be A and B, or it can be A prime and B prime. The pressure here, pressure A prime, is equal to pressure B prime because pressure at same level are equal. So pressure at A is same as pressure at B. So we can calculate pressure at A, which is equal to pressure on top plus rho, density of this fluid, height, which is 5.5, rho times 5.5 times gravity G 9.8. So pressure on top is the pressure from atmospheric pressure, which is 1.013 times 10 to 5. So atmospheric pressure plus the pressure from the fluid, which is density of the fluid, height, and gravity, which is the point A, which is exactly same as the point B. So here's your pressure 2. Here's your pressure 1. So P2 is, this is atmosphere. Atmospheric pressure, because it's on the top of the surface. So plus rho, density of water, which is 1000, and the G, which is gravity 9.8, is the height from A to the surface, which is 5.5. So pressure on the bottom or the point A is 1.55 times 10 to 5. Pressure gauges. We can make a pressure gauge to measure the atmospheric pressure or pressure at a certain place. So basically you need a container of fluid, container full of fluid, and it's very easy to make a pressure gauge. So you need a test tube filled with the same fluid, and then you turn upside down, and then you will make a pressure gauge, something like this. And when you turn it upside down, on top of the uh, tube has a small volume which doesn't contain the same fluid. So from this equation, the pressure difference, pressure at point 2, which is point A. So instead of 2, I can write point A. So pressure at point A is equal to pressure at here, let's say this point PA. So we can write P1 plus density of this fluid, gravity times H. H is the height of this fluid column. So we know this area doesn't have any air molecules, therefore the pressure is force over area. In this area, these air molecules, if there is any, put in the force. If there are no air molecules, there is no force, which means there is no pressure. So which means the pressure on top from this empty space is 0. Therefore, this term is 0. So basically, pressure at the bottom A is same as the density of the fluid, which is rho, and the G and the height, rho GH. So if you use mercury, we use the density of mercury, which is 13,000, and the gravity and the height. So to make this, so So now we know that's one point. And the second point is P2 is equal to P1 plus rho GH. And if the H is the same level, so for example, PA and PB, pressure B and pressure A. If it is same level, we know H is 0. Therefore, pressure A is same as pressure B. So therefore, if you know the pressure at A, it is same as pressure at B. Pressure at B is basically atmospheric pressure. So pressure at B, which is atmospheric pressure, which is equal to pressure at A, pressure at A is rho GH. So atmospheric pressure, the pressure here from atmosphere, air molecules, is same as the rho GH. So if you use mercury, you have to use 760 millimeters, which is 76 centimeters tall tube or mercury column to balance the force acting on the outer surface from the air molecule in the atmosphere, because that force pushes this liquid into the tube. So at one point it will balance with the atmospheric pressure. The weight is balanced with the atmospheric pressure. So this column, weight on that column is same as the atmospheric pressure rho GH. In this container, in this cube, if the pressure is greater than the outside, so if you have a liquid column, it will push because of the additional pressure, and at one point it will balance. So but we know the pressure at same level, PB, pressure at B is same as pressure at A. So pressure at A is pressure on top, which is atmospheric pressure, plus pressure at A is equal to atmospheric pressure P1 atmospheric plus rho GH is the height difference of this fluid column. So if you know the pressure here, which is equal to pressure B, which is equal to the pressure inside the cube. So pressure difference P2 minus P atmosphere is rho GH. So pressure here is same as the rho GH. And we can use this concept to make a blood pressure monitor. The blood pressure, and so the pressure outside, I mean pressure here is greater than pressure here. So this level and this level, same pressure. So the pressure difference is rho GH, which is equal to the blood pressure. Rho GH, density of the fluid, gravity, and the height of this column. Next topic is Pascal Principle. In this principle, it says, let's consider a U-shaped tube filled with some fluid, and as you notice, one side, left side of this tube has a smaller diameter compared to the right side of this tube. So if you apply a force onto one side, all the molecules put in pressure on the molecules underneath. So the fluid, the change in pressure applied to the enclosed fluid is transmitted undiminished to all the parts of the fluid. So there's no pressure loss or force loss, and all the pressure or force transmitted to the other side. So the most important aspect of this principle is you can apply a force, smaller force, and you can do large work. I will show you when I derive some equations to show you the force and on both sides, and how it related to the areas of the both sides of this tube. Okay, I'm going to show you how to derive an equation between the forces on either side of the tube, and also how the areas of the cross-section areas of left side to right side, and forces on the left side and right side. So we start with the same equation. P2 is equal to P1 plus rho GH. So if you consider the same level, we know there's no height difference, therefore H is 0, and therefore P2, pressure in this side, is equal to pressure on the left side. So pressure is force over area. Force on side 2 divided by force area on side 2 is equal to force on side 1 divided by area on the side 1. So this is side 1, this is side 2. So force over area on one side is equal to force on the area on the opposite side. So if I rearrange this equation, force on the second side, you can write force on the first side times area ratio of the second side to first side. So you can use this equation in this example. So let's assume this car is weight is 1000 newtons. So in order to keep this car in this level or in equilibrium without moving up or down, you have to apply a force, which is the second force on the second area, equal to the weight of the car, 1000 newtons. So you can keep this car at equilibrium position by applying a smaller force. If you use especially hand or something, you cannot apply a force to keep the car in equilibrium position. But because of this Pascal principle, you can change the area such a way that you can use a small force, but you still can keep the car at a constant or equilibrium position. Let's say the cross-section area A2 over here, this side is equal to 500. Okay, and let's say the cross-section area A1 is equal to 50. So what is the force 1, or the force you need to keep this car at this level? So if you use the same equation, I can rewrite force 1 is equal to force 2 times A1 over A2. I just rewrite this equation because I need to solve for F1. So F2 is 1000, A1 is 50, A2 is 500. So the ratio is 1 to 10, and therefore force is 10 times 100 is 1000. So force 1 is 100. So you just need a 100 Newton force, which is 10 times less than the weight of the car, in order to keep the car in this equilibrium. So if you have the ratio of A2 to A1 like 1000 times, then you need 1000 times smaller force. So depending on the ratio of the areas of the both sides, you can reduce the applied pressure on the opposite side to do some work. So here's another example similar to the one I done. The areas are given, or actually radius is given. So radius, if the radius is given, if it is a circle, the area is pi r square. So you have to make sure you use the right area, pi r square, for this side and this side, because the areas radius is given, and then it says the weight of the car and the plunger is 20,500. So, and now you have to calculate the required input force. So you can use the same equation on the previous page I wrote to solve this problem. So when you substitute the numbers, the weight of the car, actually this is F1 because this is F2. So it's a typo. So this is F1. This is area 1. This is area 2. So then you just need 131 Newton force to hold a 20,500 because you have a huge area ratio for the huge number for the areas, ratio of the areas on the both sides. Our next topic is Archimedes principle. Actually, the lab we're going to do today is based on Archimedes principle. So let's consider the same similar problem, same equation we used in the previous section. So we have a object uh, inside this particular fluid, and 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 we can consider the pressure or force. Pressure is force over area. So force, sorry, the force is pressure times area. So pressure here is, let's say, P2 times area is greater than pressure on top. Therefore, this object will move on to the go up. If this pressure is less than the pressure on top, it will sink. If these two are equal, it will stay at one location. So it cannot go up or down because the force on top is same as force on bottom. But this particular case, force from bottom is greater than force from top. So therefore, uh, force difference is P2A minus P1A. P2A minus P1A. So A is the cross-section area. It's common to both terms. So P2 minus P1A. So pressure 2, we can write P21 in terms of the equation. P2 minus P1 is rho GH. So I can write, so FB, the pressure difference from bottom minus top. I will tell you what this B means. Pressure, force difference between bottom and top, P2A minus P1A, is rho GH, rho GH. Okay, so rho is density. Density is mass over volume. So instead of rho, I can write M over V. Okay, and also we know V is volume, which is equal to height times cross section, HA. So once you do that, you will have rho Vg. So V equals H A G. Answer. So rho and V, rho times V is mass, mg. So Fb is mg. So we know mass times gravity is, we call it weight. So B means buoyancy. Buoyancy force, the force acting on the body, is called buoyancy force, which is equal to mass of the object times gravity. Okay, so Archimedes' principle says any fluid applies a buoyant force to an object that is partially, completely immersed in it. So in the previous example, the object is completely immersed in the fluid. So the buoyancy force acting on the body from the fluid, we call it buoyancy force. B is used for buoyant. That is equal to mg, which is the weight of the fluid, weight displaced of the fluid. So magnitude of this force equal to the weight of the fluid that displace. So weight of the fluid that displace is same as the buoyancy force. So here in part A, we see the weight of this cube is 100 Newton and buoyancy force is small. So which means weight is greater than buoyancy force. Buoyancy force B, if B. So if weight is greater, which means this object sink. In the second example, this is weight force balanced with buoyancy force. Therefore, it will completely float at this level.